So I'm going to be talking about the framework that we've developed. So the implementation we'll be doing later on, this serves as the foundation for that. Kind of quick, we're going to have to run through this fairly quickly, so we've got 15 minutes to go through this. So we developed a 5-step framework that consists of specifying the problem. So Peter's already gone through that earlier today, but I'll go through it just to really drill that in, because this is what I say is the key thing, because you want to make sure that you specified your problem correctly so you're solving the problem you want to solve and not some other prediction problem. Then it's going to be identifying the suitable data. This might not always be as flexible for you. You might only have 1 or 2 data sets or 1 data set available, but if you've got multiple data, then this is something that you might want to look into. Selecting the predictor variables. We've created standardized variables in the framework. So if you're running the PLP package, you can actually just select with a checkbox which variables you want. You can also add in custom covariates if you want to do your own R stuff. Then it's going to be selecting the models. Peter's already mentioned some of the models. There's a few additional ones that I'll go through, and I'll talk about the different models and give a brief overview of actually what you're doing when you're training the model. And then we go into the validation. So to specify the problem, the aim is to use our standardized definition of within some target population, which is the people you want to do the prediction, predict some outcome during some time at risk. So you need to specify your target population and the outcome and the time at risk. Now, there's been a few questions about the T0. The way I think of it is T0 is if you're implementing this model, what point in time would you be implementing this model? So would it be when someone comes to the doctor and they have a certain condition? Would it be when they come to the doctor for some annual checkup? That's your T0. And then your time at risk is going to be some point in the future relative to that time 0. The benefit of having this whole standardized problem definition is that we want it to be transparent. So if you write a paper and you've written this problem in this format, anyone who looks at it can see what you're actually predicting. Then we want to identify the suitable data. So this again, it depends how much data sets you actually have available to you. But you want to make sure that your target population is sufficiently sized in the data you're looking at. You want to make sure you've got enough outcomes. So there's been quite a lot of papers that have been criticizing that sometimes you don't necessarily have enough outcomes. So when you're building a model, that could be problematic. And also if you're validating, you don't have enough outcomes, that can be problematic. And then you also want to see, does it have the variables that might be informative and ability to actually predict in the data set you've got. So as an example of if you were trying to use a data set that had older populations, like some Medicare type of data, you probably don't want to do something that's predicting some outcome in pregnancy because you're not going to have pregnant people. So that's something to be aware of. Select the predictor variables. We've actually got some standardized variables already in the package, so you can readily just select any conditions, drugs, procedures, measurements, observations, demographics. There's some risk scores already in there, and like variables that correspond to healthcare utility, they're all in there. You can also create your own variables, so if you wanted to look for specific sets of concepts, or you want to look at a specific time period, you can actually create that in our package. Our package is very flexible for enabling you to create your own variables and your own models if that's needed. Select the models. Again, we've got the standardized models. So we've got gradient boosting, we've got random forest, we've got lasso logistic regression, we've got various other boosting algorithms, KNN, if you want to use that. KNN is a bit of a harder one because it's hard to share that model across the network. So if you wanted to do a model that you wanted to externally validate, KNN is going to be very difficult because you need the data for that, and most people can't share their data. We've also got deep learning being added. So Peter's been working on deep learning, and that is on the GitHub as a different branch, and that will soon be added into the main GitHub. So when you actually download patient level prediction in a few months, there should be deep learning in there. Now these are the current models that we've got in the patient level prediction package. So as a best practice, as well, Peter mentioned earlier that it's worth just running them all, whether there's an order, it's up to you which order you put them. We suggest, because it's actually generally quite quick to run these algorithms, but assuming you've got a day or so to do these models, you could probably just apply them, all of these, and see which one does best. It obviously depends on your hyperparameter search, the time. So the default settings, it's quite quick. If you made a very big grid for your hyperparameter search, it could take some time for some of these models. So what is the aim of training a model? Well, if you imagine your people and their variables to give you a point in space for everyone you've got, and then you've either got people who have the outcome during your time at risk and people who don't have the outcome during the time at risk. The whole aim of learning a model is just to learn this decision boundary. So, and then the aim is to then, when you've got a new person, where do they fall on that decision? Do they fall into people who don't have the outcome? Do they fall into people who have the outcome? So this is what every model is basically doing when you're training it. Now the hyperparameters, so
could you go back to that slide? And what I need to understand this is, can you reframe it? Can somebody sort of reframe it in terms of a clinical statement? Like, are we discriminating? Is the decision boundary about the patient who does versus doesn't develop an outcome? Is that it?
So yeah, so if you think about, so the way you can look at that is the people in blue, these might be the people who have the outcome during your time at risk. People in red are people who don't have the outcome during your time at risk. So everyone we've got the high dimensional space, it's going to be hard to visualize, so we've just got the 2 dimensions here. Everyone can be thought of as represented as a dot in that space. And your aim is to just find some sort of functional, some hyperplane that partitions the people. And then ideally that would generalize to new data. So this is what we do when we do the external validation, is to make sure it generalizes. So when people talk about modeling, you hear hyperparameters and you hear parameters of a model. Some people kind of put them all together and think they're the same thing. The hyperparameters effectively control how complex your model is. So a decision tree could be very simple, where you're saying I only want to look at kind of 1 interaction, or it could be very complex when you want to look at 20 interactions. So the depth of your decision tree is a hyperparameter. So when you're picking a model, depending on how complex your prediction problem is that's going to define which hyperparameters are optimal. So the first thing you want to do when you're training a model is actually identify the hyperparameters, so the complexity of your specific classifier. And then once you've defined that, you then train it on the data and calculate the actual parameters. So for the lasso listed regression, the hyperparameter is the regularizer, so how much regularization are you doing? And again, that will depend on the data you've got. With neural network, it will be the topology of your network. That will kind of define how complex, and you can add in regularizers and such. So just to kind of go over this a bit more, when you're actually training your model, you have this bias and variance. So bias is effectively, it's a simple model, it's highly biased. It's a very complex model, it's going to be less biased, but it could have a high variance and you might overfit. So as you go in the model complexity, your bias reduces, but your variance goes up. And as you've got kind of a very simple, you've got a high bias and low variance. So depending on your data, you want to find the trade-off that is best for this. So the hyperparameters effectively, so most models, you can kind of go for a range of this. The hyperparameter is going to pick the point, which is like the nice bit, which is you're going to get some good models out. So this is what you're doing when you're selecting your hyperparameters. So this is basically too simple. This is overfitting. This is just right.
And Jenna, we decide that, or the model will just figure it out by trying to figure it out?
So when we train the model, and you say you're doing cross-validation, when you pick when you're doing the cross-validation, it's actually doing cross-validation for every hyperparameter setting that you've put in. So you'll see later that we do a grid search for a lot of our algorithms, where you say, I want to look for each of the hyperparameters of the model. Here's all the things I want to, like values I want to look at. It then looks at every combination of those, creates a model doing the n-fold cross-validation for every combination, and then it picks which one did best and says, okay, this setting of hyperparameters was basically this point here, assuming that we can actually do extensive search. Sometimes you might just want to be quick and just say, I'm just going to take a few points and just pick the ones that seem to do the best, the ones I picked, a search tree.
Well, so I repeat this question. The package does that, or you say you just pick? I don't want to pick. I want the sheet.
So the package has default settings for the hyperparameter grid search. But and the way I've done it is I've picked the ones that generally do well. So for random forest, for example, the number of variables you put into each model as in general is the square root of the number of variables that you have is a good value. And changing that doesn't generally make a big impact. So the default setting in the PLP packages is to have that as the set value. And then the depth of the decision tree might be 2, 4, and 17. So it gives you a range of complexities. So that's the default settings, and they're generally picked so that they should do well and they should be very quick to run. But if you wanted to say, I want to do a more extensive search, you could say, I want to look at an mtry of 5, all the way up to the number of variables I have with like steps of 5. And I could look at every single depth available up to 100. And then it's going to make a very big grid of every combination of those. So it's going to take a long time to train and pick the best settings. But it should then, you can be more confident that you have picked the best model that you can for your data set. Rather than right now, you're getting in the ballpark figure. It's probably not going to deviate too much, but you probably could do some improvement if you did a bigger search. So this is just a visualization of what you're doing when you're training. So you can see here, if you had this data set, a linear model would be too simple. A very high order polynomial would be too complex because you're overfitting. This could be noise. So this might not generalize well. If you had a new data point here that was a circle, you would misclassify that, or you get that wrong because you've overfit to the noise. Whereas this seems to be the right complexity for this data set. So the hyperparameters are basically just figuring out how complex your model should be. Now the decision boundaries differ for each algorithm. This is why we suggest that you should try as many algorithms as you can, and time kind of provides. Because, for example, decision tree, they actually do vertical and horizontal boundaries only. Neural network have slightly different boundaries. Random forest is a bit more fuzzy because you're combining lots of decision trees together. So depending on your data, the boundary is going to, the optimal one's going to be different because it all really depends on these boundaries. Now the nice thing that about the OHDSI network is that we can do very extensive external validation. So we do when we're doing the model training, we have the train test split put in. So we do this the n-fold cross validation to find the hyperparameters. We then apply it to the test set. So this is the data that's never used to train the model. It's just used to validate the model. And this gives you your internal validation. So you'll get this out when you apply the PLP package. You'll get the test and train set performance. But then we actually provide a code that enables you to very readily run these models across any data set that is in the common data model format. So you can externally validate it very quickly across our network, which is a big advantage because the way models are done at the moment, it can often take up to 3 years before a model gets externally validated. And I think we can improve that quite a lot. So that's a good thing to go into. So does anyone have any other questions about this framework?
So I understand there's the 2 parameters to pick. One is the split, like 75% training, 25% testing, and then the number of folds. So there are just 2 numbers where I set that, or how do I do this?
Yeah, so in the code, so in Atlas or in R, whichever way you want to run it, there'll be the split type, which will be whether you want to do a patient or a time split. So this is another thing. So you can actually split the data temporally. So if you have temporal changes, you can see if that's affected, or you can do just a random person split, where you just randomly divide people on people, and then you say the percentage that you want into the test set between 0 and 100. I think it says you've got an error if you go any other value of that. And then for the folds, again, it will say number of folds. I think it's n-fold is the parameter, and you can put in any value greater than 1 or 2. It should come up. If you put invalid values, it should come up as a warning or an error. So these are just 3 parameters you just need to put in, and we'll see that later on in Atlas, and then you can play around with that later on when you're actually doing it interactively.
For sharing it with other sites that you've done something, is there a JSON object at the end that you say this is how I define my T and my O, and this is the settings I chose for my hyperparameters and the number of models I ran? Is that able to be encapsulated in a shareable form?
Yeah, so when you run the model, it will save all the parameters that you've actually entered for anything. The T and the O are a bit harder to share because that's generally done either SQL code manually or using Atlas. But we have got code that you can run that extracts. If you've done it in Atlas, for example, it will extract as a JSON object the creation of the cohorts. So when I try and share models, I just use the output from the framework, and then I run that code to get the JSON. So then it will create the cohorts for people as well.
So to follow up on that, so I already peeked at the R code generated in Atlas. So one thing which would be very helpful that there's this common Atlas instance, and I can refer to IDs there. So I can see it says target node ID and 113.2116. Is that correctly going to go to my local host where I'm running this, my Atlas, or is it going to go to the global OHDSI phenotype repository?
So if you're running it, so say we had the JSON files to create the cohorts.
I actually want to avoid those because when I distribute my package, that means the site is to rebuild that package from scratch. It's not going to work at that site.
So it means that they'd have to recreate the cohorts. So they would have to kind of basically call that SQL to generate the cohorts on their data. And then once that's done, it will just run the code that's already been, like the model that's already been developed, which will be applied to them. But there's no easy way of sharing the SQL at the moment. So in Atlas internally for J&J, for example, we've got the Atlas connected to all our data sets. We can just say generate on everything that we've got, and it will then create the cohorts. And then I can run the code easily. But to share the model, you're going to have to share the SQL and get them to rerun that on their data. So they actually have the same cohorts. Unless if there's an idea of being able to easily share the SQL.
I can fine.